Time-of-flight imaging systems are being used in many depth sensing applications. Continuous wave time-of-flight systems are particularly attractive due to their low power and low cost requirements. Continuous wave time-of-flight cameras work by periodically modulating the intensity of a light source according to the source modulation function. The radiance incident on the sensor is correlated with the sensor demodulation function. 3 or more intensity measurements are captured for estimating scene depths. For a given hardware and imaging setting, the performance of a time-of-flight camera is determined by its modulation and demodulation functions, also referred as decoding functions. Most current cameras use sinusoid coding where both modulation and demodulation functions are sinusoids. The resulting correlation functions are also sinusoids. Although sinusoid and square coding functions are easy to implement on existing hardware platforms, their performance in terms of depth precision is relatively low. There has been recent work on developing high-performance time-of-flight coding functions. Although these novel functions can theoretically achieve very high depth resolution, their hardware implementation remains impractical. This is because these functions require an impulse modulation function with infinite peak power and large bandwidth. Furthermore, these functions are continuous valued and thus difficult to implement on current hardware with digital signal generation. In this paper, our goal is to design practical and yet high-performance coding functions. We pose the practical code design problem as a constraint optimization problem with the following constraints. The modulation function should have a finite peak power. The maximum power of a light source is a common specification given by a manufacturer. The modulation and demodulation functions should be binary. This constraint follows from the fact that most time-of-flight cameras rely on digitally generated square wave signals. Finally, the output modulation and demodulation functions should adhere to the system's band limits. While the input functions given to the system are required to be binary, the output functions after passing through the system have a limited bandwidth. So, the binary constraint is applied on the input functions, whereas the band limit constraint is applied on the output functions. The output functions produce the final correlation functions. As an example, we apply our approach to the Hamiltonian coding function family with a pre-specified set of hardware constraints. These are the final output modulation and demodulation functions and the resulting correlation functions. Here's another example with a different set of constraints. The proposed functions adhere to the practical constraints with only a small loss in performance with respect to the previous functions. The proposed approach can be used to design codes for any given set of hardware constraints. Here is a comparison under a relatively strong set of constraints, where the peak power and bandwidth are limited. The resulting codes achieve higher depth estimation accuracy under a wide range of SNR levels. In summary, we have developed a simple and flexible approach for designing practical time-of-flight codes. We designed example coding schemes and demonstrated their performance benefits. The proposed approach can provide a general recipe for designing novel high-performance time-of-flight codes in the future that adhere to specific hardware constraints imposed by a given platform.